In a periodic crystal, an electron exists as a wave, stretching across the entire lattice. To map these wave states accurately, we move beyond physical coordinates and analyze them in momentum space, or K-space. Our starting point is a perfect two-dimensional crystal. We define the atoms as sitting on a square grid, separated by a repeating distance, a lattice spacing we call A. When we translate that repeating physical grid into reciprocal space, the geometry inverts. The boundary of this momentum space extends from negative pi over A to positive pi over A, forming the first Brillouin zone. This square is the essential repeating map. It contains the complete set of unique quantum wave vectors allowed for an electron within this specific crystal lattice. Within this grid, electrons hop between neighboring atoms. Using the tight binding model, we see how energy depends explicitly on momentum coordinates. This 3D surface maps the dispersion equation inside the Brillouin zone. Electrons fill the lowest states up to the Fermi energy, separating occupied from unoccupied. Their intersection forms the Fermi surface, initially circular, warping as it expands toward the boundaries. The topology of this boundary determines how the material responds to external fields. Only the electrons sitting on this surface have the available momentum to move, governing the macroscopic electronic properties of the material. To see how these states are distributed, we look at the density of states. This is a strict accounting of how many available quantum states exist within a specific energy interval. This split screen tracks the energy surface against the density of states. Where energy changes slowly across K-space, available states pile up. This is extreme at saddle points, triggering a sharp spike in states, known as a Van Hove singularity. This entire map relies on a static atomic grid. We must determine how this landscape reacts when the physical periodicity expands. Physical structures often change through layered growth or charge density waves. When the crystal lattice shifts to create a larger repeating unit, we see an expansion of periodicity in real space. The geometric rule connecting these spaces is fixed. Enlarging the boundaries in real space mandates a tighter, smaller reciprocal space architecture. Under the law of state conservation, altering spatial boundaries cannot create or destroy electron states. If a one-dimensional unit cell doubles in real space, the allowed momentum points halve. To compensate, the energy bands must double, perfectly maintaining the total state inventory. Because the total number of states is identical, the system uses a relabeling algorithm to fit the original states into the newly restricted zone. We can observe this mechanical process by shrinking the Brillouin zone boundaries on a standard parabolic dispersion curve. States that suddenly fall outside the new, contracted boundaries are physically folded back inward. They reflect across the new limit, populating the smaller reciprocal zone. The mathematical operation behind this fold involves shifting the original states by subtracting the new reciprocal lattice vector, G nu. This results in the original unshifted band, the blue curve, coexisting with the new folded branch. The two bands cross exactly at the edge of the new boundary. Band folding acts as a superimposition. It is a mathematical relabeling that fits extended states into a compressed reciprocal volume. This same logic scales up to 2D systems, particularly in computational density functional theory, where researchers often employ artificial super-subparticle calculation convenience. Expanding a unit cell to an n by n area shrinks the Brillouin zone by an inverse factor of n squared. The original 3D energy surface shatters and stacks into n squared folded branches. This creates a densely packed momentum space where multiple energy bands overlap. While this creates a complex architecture of crossing bands, these bands pass through each other without interacting because the underlying Hamiltonian of the system remains unchanged. There is a vital distinction between setting up a convenient computational boundary and observing a genuine physical transition in a material. This split table highlights the difference. Artificial folding is a change in bookkeeping, while physical folding occurs when a material develops a genuine new periodicity. Real transitions, like magnetic ordering, introduce a new periodic potential to the system, fundamentally altering the physical rules. This periodic potential changes how the mathematically folded bands interact. They are no longer independent. they begin to feel the presence of one another. This macroview graph shows where folded energy bands intersect. In an artificial supercell, these bands pass cleanly through each other. But in a physical system, the new potential creates a coupling matrix element, forcing the two states to hybridize. The bands repel in an anti-crossing maneuver, pushing the energy levels apart and opening a measurable mini-gap. This transformation turns a mathematical intersection into a physical energy barrier, altering the material's conductivity and thermodynamic properties. We can observe these architectures directly using RPs, where photons strike a crystal surface and cause electrons to be ejected into a detector lens. The experimental data reveals faint shifted shadow traces, known as replica bands. These are the physical evidence of the new reciprocal lattice vectors. In the mini-gaps panel, we see the characteristic split where the theoretical hybridization actually tears the bands apart. This five-step process summarizes the journey. A larger real space period creates a smaller Brillouin zone, which forces states to fold and interact. Band folding maps the mathematical consequence of changing spatial periodicity. It illustrates how the geometric arrangement of atoms dictates the allowed energy states and electronic behavior of the material.